Hello everyone, my name is Mogan Gim, and today I would like to orally present my paper called MolPLA, a molecular pre-training framework for learning cores, R groups, and their linker joints. So this paper was recently published in Bioinformatics, so if you want to check it out, all you have to do is just Google MolPLA, and you will get the search results as above. Okay, so today I would like to talk about the three key points in this presentation. First of all, I would like to talk about the motivation behind using the concepts of cores, R groups, and linker joints, starting from the study ideation to pre-training dataset construction. And next, I would like to talk about the in-depth explanation about MLPLA, which is our pre-training framework, by talking about the central motivation to specific model design choices. And last but not least, I would like to mention some limitations and the future direction of MLPLA towards more robust and efficient molecule generation using graphs. Okay, so as you know, there are so many drug discovery tasks which could be tackled by different types of computational methods, starting from adamant prediction to one of the hardest challenges like drug generation. So all of these tasks have one common feature, and is that the central component of these drug discovery downstream tasks revolve around molecular representation learning, meaning that all of these performances depend on how much the model really knows about each of the characteristics of the molecules. So one straightforward approach to improve the performance of these tasks is to exploit pre-training. So starting from pre-training some kind of a foundational backbone on a massively large number of molecules, and then you get to fine-tune them and then on a specific downstream application, such as property prediction or molecule generation. And learning molecular features is more about related to how to guide the model's characterization of the molecule. So a molecule can be characterized in various ways. It could be characterized as a set of atoms connected by bonds or some Cartesian coordinates, or even by their circular atom neighborhoods, or even a single-handed multi-dimensional bioactivity profile. But what we really wanted to focus on is to help the model learn about the structural aspects of the compounds. So for example, a set of fragments decomposed by some kind of a special algorithm like bricks or recap, or a set of cores in which they have other names like scaffolds or templates, and R groups, which are also called as isosteres or functional groups or motifs. So basically, molecular fragmentalization involves decomposing the molecule into fragments by cutting its bonds, which are also regulated by a set of chemical rules. So if you look on the right side, you can notice that this compound can be conceptually described as a set of fragments. And on the other hand, molecular core identification involves identifying the core part of the molecule, while regarding the peripheral parts as R groups. But they are still connected to each other because they haven't been decomposed yet, because we only know that which regions correspond to the core structure of that molecule. So one of the motivational related works that helped us design our study is the paper called Fragment-Based Dual-Channel Pre-Training, which was published in the BMC Bioinformatics Journal. And the concept is pretty simple. All you have, the authors of this paper used contrastive learning between a full original complete graph and a set of fragment-wise subgraphs which are aggregated into one single representation. So we ask ourselves this question: what if we apply the notion of molecular cores to decomposition? Meaning that why don't we just cut the bonds between the scaffold and the other rest of the R groups? So that our initial sketch of our development phase was to somehow adopt the approaches from Frel and try to modify it into more of the architecture that actually uses our core-based approach. But however, during our early feedback, there were two critical questions. First one is, okay, viewing the molecules as scaffold and functional arms is pretty cool, but what is the significance of it, the novelty and the impact of it? And also, the widely used algorithm for identifying these core structures, scaffolds, is the Bemis-Merkle scaffold, but it is not that practical, and that is, fragments seem to be better. So how are we going to respond to this? So we had to look for some cheminformatics papers because we felt that there's a better way to extract the core structures from a bunch of molecules. And we found Navea's paper, which was published in the Journals of Cheminformatics, which is titled A General Approach for Retrosynthetic Molecular Core Analysis. So what this paper does is that it actually highlights the limitations of the Bemis-Merkel scaffolds, and it also proposes an alternative framework called the putative core framework. So there are lots of advantages. First of all, the number of cores per molecule could be one or more, and unlike the Bemis-Merkel scaffolds, rings can be substituents. And also, it actually considers the retrosynthetic rules while doing the putative core framework. So the definition of the putative core is based on two criteria. The first one is related to the relevance criterion, and the second one is related to the synthetic feasibility criterion. This provided a strong justification for us to utilize Navea's putative core framework into identifying the core structures of the compounds. So we have a very extreme example of the difference between the Merkel scaffolds and the Navea's core framework. So let's say this molecule looks like this, and if we apply the Bemis-Merkel scaffold, the Merkel scaffold is the molecule itself. But when we apply the Navea's core framework, we get to have different forms of putative cores and also different decomposition results, which we're going to explain later. This is one of the strong advantages of us utilizing the Navea's putative core framework. So how are we supposed to decompose the molecule, given that we have the putative cores identified? There are actually two commonly used methods. First one is bond cleavage. You get to just cut the bonds, or linker detachment, just detaching the linker. But we wanted to somehow receive more inspiration from another common graph representation learning technique called mask and reconstruction. So basically, you get to randomly mask the attributes of the atoms or the bonds, and you encourage the model to reconstruct them during the pre-training phase. So what we wanted to do is we propose a unique approach for decomposition called decoupling and masking, which results in mask linker joints. So imagine that these two graphs are connected by one single atom, and you just decouple it. And while you decouple it, you also mask the commonly shared linker node and also the connected linker edges as well. So like I said before, the R groups are decoupled from the core based on their shared linker nodes. And the original attributes of the linker node and its connected edges, known as linker joints, are masked during the decomposition process. So our first rationale for this particular technique is that we were already acknowledged the advantages of mask graph representation learning, so we wanted to use it. And there's another justification for this approach, which I will explain later. So as a result, given the geome dataset as our main source dataset, we get to extract the putative cores and the R groups. And if you look at the R groups on the right side, you can notice that there are also ring-like substituents as well. And so once we get to do the decomposition, you may notice that we get to have one single putative core with 3 different R groups, but we don't have to detach all the R groups. We can detach a subset of R groups. That is, we can actually build a total number of 7 different possibilities of decomposition. So you have one molecule and 3 different putative cores and 7 decomposition results for one particular putative core. So basically, if you're given 300,000 drug-like molecules, you can actually make over 1 million of decomposition results. So that was the end of our dataset construction. Now we're going to move on to the real deal of what MolPLA actually looks like and why we designed it that way. So in order to justify the purpose of the pre-training, we have to basically show that it empirically works in some kind of specific downstream task, which we set the downstream task as property prediction. But we wanted to show more value to it. So that is the main essence of our work. So this is the MolPLA framework, and it actually consists of 2 different frameworks, which one is called the mask contrastive learning framework, which consists of F theta as the graph encoder, G theta as the graph projection head, and G kappa as the node projection head. And the other framework is called the R group retrieval framework, which I will explain a little bit in detail. So for the propagation and how to how to use this framework, well, you're given two different types of representations. The first one is original molecular graph, and the second one is the decomposed molecular graph. And the decomposed molecular graph is actually a set of disjoint subgraphs, meaning that the node embeddings are in the same tensor, but the edge index indicates that the subgraphs are disjoint. So you basically propagate two different graphs through the same graph encoder, which you have on the top side, the node embeddings of the actual original graph, and the mixed set of node embeddings which are the masked ones and the unmasked ones from the decomposed molecular graph. And then you get to just aggregate it through a readout function using mean pooling, and you get two graph representations, and you get to plug into the contrastive loss so that the model learns the decomposable features of that molecule. And I'll explain more about the Argo retrieval later on. So the purpose of the first loss function, which is a graph contrastive loss, is to help the molecule characterize the global structure of a molecule based on its decomposable regions. And the second one is more indeed focuses more on helping the molecule identify the potential decomposable linker joints, meaning that once we're given two different node representations and plug it into the contrastive loss, we get to help the molecule identify which nodes are prone to be decomposed, which will be further used in other tasks. And the third one loss is related to the Argo retrieval loss. And what we're trying to do is to add another task, which is called Argo retrieval. This one helps the molecule learn how to retrieve R groups that are suitable to the mass linker joints of the given query template. So let's say that I detach the R groups from the current molecule. Now I have in that detached form, we get to have two different mass linker joints. And I want to retrieve some better R groups that can actually optimize the compound itself. This is what the R group retrieval framework does. It takes the input represented as a query template with mass linker joints, and then it actually projects the node representation to the co-embedding space where there are a bunch of other R groups as well. And this will be used in our leaf optimization scenario, which will be also explained later. So this is the experimental results of our molecular property prediction task, which we use the pre-trained graph encoder and fine-tune it on the downstream task, which according to results, our model performed better than other baselines. And another downstream task is called lead optimization, which we exploited the node features based on these coloring results and first identified the linker joints of the out-of-dataset drugs and performed re-optimization by retrieving the R groups that can help improve the molecule's properties. This is a more in detail description of how it actually works. We basically project all the R groups from our library into the co-embedding space so that we can perform vector similarity search. And this is another reason why we get to use mass linker joints, because it actually provides flexibility by reverse processing the decoupling, meaning that we want to attach another R group to the current query template, we get to automatically designate the atom and bond types via using the RDKL library. That is the second reason why we use the mass linker joints. And so this is the results of the lead optimization. And lastly, I would like to point out the real purpose of MolPLA is this preliminary step towards our way of molecular generation. And I would like to also talk, and there are also the unsolved limitations, like for example, the quantitative results were kind of unsatisfactory, and requires a lot of effort of post-processing. And our Argo retrieval framework is actually based on more related to ligand drug design based rather than structure-based drug design. And we are still uncertain whether this is a promising alternative to other generation models that basically use diffusion. And for future work, we are planning to do this. And I would like to express my gratitude toward my colleagues, especially Juwon Park and Soyoung Park, who dedicated themselves in making this awesome work, and also Professor Jeo Kang, who is my principal investigator. And I also like to thank the ISMB staff and the committee for giving me this great opportunity to present this work. So thank you very much for your attention.
Thank you very much. We have time for a few questions. So maybe I can start with one. You mentioned in the beginning that one of the main reasons that you're looking for better representations is some of the downstream tasks that you also mentioned. One of them was binding affinity optimization and prediction. Maybe I missed it, but have you tried your new representation on binding affinity prediction, or do you have plans on performing that kind of task?
Actually, we are trying to improve our current pre-training framework and to make it into another publication. And so we're trying to make it more like a foundational model so that we can apply it to the other downstream tests like binding affinity prediction, like you mentioned. This framework is actually tailored for molecular reassembly and property prediction, but we're trying to improve it so that we can make it a more useful model, which has more several advantages compared to other GPU heavy models. Yeah.
Right, thanks.